Welcome back from winter break. I hope the time you had off was relaxing and enjoyable. Welcome back to school. We are going to start chapter 5 in this new year, and we're going to start with section 5.2. We're going to split it up into 2 days, kind of do a little bit of notes and then some group work, and then notes tomorrow and finish up the group work, just kind of to ease back into the swing of things. So the first section of chapter 5 is called Linear Approximations and Differentials. And we've actually been dealing with this quite a bit. We just haven't given certain parts the names and vocabulary that we are going to be using this chapter. So here's a graph of a function f as well as its tangent line. We're going to start calling that function L. And you can see it is at the x value of c. That's called our fixed point. So that's the point at which we have our tangent line drawn. And there's a couple of different parts that we are going to label this graph with. So the very first thing is when you make like a slope triangle from the fixed point C to another x value, okay, the difference between the fixed point and another x value is called delta x. The slope triangle that we've created with our tangent line, that is our m equals dy dx, that's our slope, our derivative. And if I broke it down into the slope triangle, our dy is our rise, and our dx is our run. And those are called differentials. So this is a new vocabulary term, differentials. And we're going to be using those terms in this chapter as well as what's coming up in the next couple of sections. And we talk about dy being the approximate change in y. So not the actual change in y because we're only using the tangent line. The full distance from the y value at the fixed point to the y value on the curve of f, that's called delta y, and that's the actual change in y. And so you can see we've got 2 points here. We have 1 point on the function f, we have another point on the tangent line, L, and those are 2 different y values. And there's a term for what happens to a graph as you zoom in more and more and more, and it becomes locally linear. So if you were to graph the function and the line and zoom in more and more, it looks like the line and the function are becoming one. And so we call that locally linear. And with that property, we can actually use the tangent line to approximate y values. So if we're not given what the function equation is, but we know the equation of the tangent line, we can use that to find specified y values. And then also the other part on the tangent line, the f of c plus dy, that was on the tangent line, not on the function. And then if we're going to be using our tangent line to calculate approximations of y values, you're obviously not going to get the exact value. And so as you get farther and farther away, you'll notice the distance between the function and the tangent line grow farther and farther apart. But as you get closer and closer to that fixed point, the distance between the two, the curve f and the line L, gets smaller and smaller as you get closer to C. And we're going to be concerned with calculating what we call the error. And the error is that distance between the function and the tangent line. And you can calculate it in 2 different ways. If you know your function, you can find it at whatever your x value is, so f of x, and then you subtract the y value on the tangent line and you take the absolute value of that because errors are just going to be positive values. The closer your error is to 0, the good approximation that your number is. The other way that you could find it is the absolute value of the difference between dy and delta y. So the approximate change in y and the actual change in y also gives you that same little distance for calculating the error. So as I said before, if a function f is differentiable at a point, then it is also what we call locally linear there. So we can use the tangent line if we're not given the function to approximate y values along the curve. So in our first example, there's going to be questions that are going to start coming up that sound a little different than what we've heard before, but they're asking something that you have already done before. So for example, for f of x equals 15 minus x cubed, it says find the particular equation for L of x, the linear function whose graph is tangent to the graph of f at the fixed point 2, 7. All of that is just fancy for saying write the equation of the tangent line at the point 2, 7. So this is something we've already done before. The only difference is now they're probably going to say something about the linear function and find the approximation using the line of best fit at the point. And now we're going to be using L of x instead of our y minus y1. We're still going to use point slope form, but we are going to be using L of x because we're going to give the tangent line its own name, its own function. And so in doing so, now we were already given the point, so you didn't have to plug in 2. We were given the point 2, 7, but just wanted to make sure it comes out okay. So 15 minus 8 is 7. The next thing we need to do is find the slope, find the derivative of f. We get negative 3x squared. So f prime of 2, when you plug 2 in, you get 2 squared is 4. 4 times negative 3 is negative 12. When you write out the line in point slope form, it's L of x minus 7 equals negative 12 times x minus 2. And then because we're going to be using this, it might be easiest to bring the 7 over to the other side. You can either put it in the front or put it at the back because we're going to be using this equation to approximate y values around our fixed point. But before we do that, I want to break down this linear equation into different parts, and some things are gonna there's gonna be some new vocabulary here. So the first thing is, this isn't new, 2 is the value of x equals c. We call that the fixed point. That's the point that has the tangent line attached to it. 7 is f of 2, that's f of c at the fixed point. That's just the y value at that value. Negative 12 is f prime of 2, the value of the derivative at the fixed point. So notice all of these things revolve around the x value of 2. The things that are going to come out to be a little different is what does that x minus 2 mean? And that x minus 2 is what we call the differential dx. That is our change in x along the tangent line. So the differential dx is the horizontal displacement of x from the fixed point. And then the negative 12 times x minus 2 is the differential dy. That's the vertical displacement from the fixed point to the point on the tangent line. And so one thing, dx and delta x are always the same, but as I talked about in the picture of the graph, dy and delta y are two different things. So what we're going to do, using our example, the 15 minus x cubed, I want to show numerically that the equation of the tangent line is a close approximation to f of x for values close to 2 by calculating the error in the approximation. And so what I want you to do is I want you to put f of x into your y1 in your calculator. That was 15 minus x cubed. And then I want you to put the equation of the tangent line in your y2. That was the negative 12 times x minus 2 plus 7. Make sure to bring that 7 over. Don't leave it on the other side. And then in your y3, you can do the calculation of the error. And so then you have to hit your math button, arrow over to num, and the first option is absolute value. And then you can do absolute value of y1 minus y2, and that's going to give you the error. These are the values I want you to plug into your calculator, so use your ask feature in your calculator. So go ahead and pause the video. So calculate the y values on the function, those y values on the tangent line, and then see how close this tangent line is to an approximation for calculating y values by looking at the errors. And so just remember, the closer the error is to 0, the better the approximation. Okay, so after giving you guys some time to plug those into your calculator, these are the values you should have come up with. My f of x values, I kept them exact. They only went out to 6 decimal places, so I didn't really do any rounding. So there are my y values on the curve, so on that cubic function. My tangent line, remember, is just an equation. It's an approximation of my y values, so these don't go out very far with decimals. And then the error is the absolute value of the f of x minus L of x. And so notice at 1.9, if I'm going to use the tangent line to calculate the y value, I get 8.2, but the actual y value is 8.141, and that's an error of 0.059. So it's close, but as you get closer and closer to 2, it becomes locally linear, and so the function and the line start matching up. And so as you can see, getting closer and closer to 2, your error is getting close to 0. And so it's a good approximation of the line. If these values had been bigger, like 0.1 and 0.2 and maybe even 2, 3, 4, it means your tangent line is not a good calculation or not a good source to use to approximate the y values. So let's walk through another example of linear approximation. So given f of x equals sine of x, make sure your calculator is in radian mode. I want you to go through these 4 things. So go ahead and pause the video. What I want you to do is write an equation for the linear function L of x that best fits at x equals 1. That's just the same thing as find the equation of the tangent line at x equals 1. Then use the linear function, use that tangent line to approximate the y value. So it says approximate f of 1.02. We're not going to plug 1.02 into the sine of x. We're going to plug it into the tangent line. Excuse me. And then calculate the error. And then find the values of dx, dy, delta x, and delta y. So go ahead and pause the video and come back and see the answers. So you were to come up with the equation of the line of best fit, or the tangent line at the point x equals 1. Remember, 1 is the fixed point. And so here is my point slope form, and then the last thing I do is I add that 0.84147 to the other side. Because when I'm going to be calculating my approximation, I want everything over. So for number 2, it said use the linear function to approximate f of 1.02. When you plug 1.02 into the tangent line, you get a value of 0.852276. The third step, you were to calculate the error, and so that is the absolute value of the difference between the actual y value and the approximate y value, and you get 0.000168. So very close approximation there. And then the last thing you were to do were to calculate the values of dx, dy, delta x, and delta y. So the one thing here is that dx and delta x are always going to be exactly the same thing. It's that run, your rise over your run. So it's the run part. It's your horizontal displacement from your fixed point, and these two will always be the same. 1.02 minus 1, you get 0.02. dy is your f prime times your dx. So it's that part of the equation of the tangent line where you have your slope and then times your x minus 1. And so in this case, I can just put in 0.02 for my dx. My f prime of 1 was 0.5403. When you multiply those together, you get 0.010806. And then the last one, so dy is an approximate change in y. Delta y is the actual change in y on the curve itself. So on the sine function, you find f of 1.02 minus f of 1, and you get 0.010637. Had our x value been lower, you always do f of x minus f of c, and so it would come out to be a negative value in your change because you are going lower than the fixed point. And so it's okay to have a delta x be negative. That just means you're moving to the left of the fixed point. It's okay to have a delta y be negative because that means you're moving lower than the fixed point instead of higher. And so go ahead and get the Linear Approximations Partner Practice Worksheet. And today you are just going to be completing the front side. So work in partners. You can check the answer key to see how well things are coming along. You're just going to be writing equations of tangent lines, calculating errors, and finding some dy dx's. Have a good day.